All right, so today's topic is lightweight stream ciphers. So I will first describe what a stream cipher is, what are the types of stream ciphers. Then I will talk about some broken stream ciphers like RC4, A51, Crypto1. And then I will talk about some unbroken stream ciphers like Cha-Cha-20, and also mention some ISO standard stream ciphers, lightweight stream standards, and Anacora and Trivium. So let's start with the definition. So you might wonder why we have a stream cipher historically. I mean, think about block ciphers. We have block ciphers because in the past we tried to modify, for instance, one letter with another letter, then realized that it can be broken by frequency analysis. Then we designed algorithms that transformed group of letters to another group of letters. So this actually introduces us the idea of block ciphers because now we are grouping the input and then perform encryption. So a similar idea actually comes for stream ciphers. In the past, we had an idea called one-time pad or random cipher, and this is unbreakable cipher. So nobody can break it, but it is not practical. I will explain what this is, then I will explain how we can modify this idea to make it practical, and this way we will introduce stream ciphers, okay? So let me first explain what a one-time pad is. So idea is as follows. You generate a very long sequence of random bits, and you write it on a single piece of page. This is why we call it one-time pad. And they have to be random. And it has to be really long, because if you want to, for instance, transmit 1,000 bits, then your one-time pad also should be at least 1,000 bits, okay? And you give it to the person you want to communicate in a secure way. Then when you want to send a message, you XOR your plain text with this one-time pad and obtain the ciphertext. So encryption is just an XOR operation. And the person who receives the ciphertext, they also XOR it with your one-time pad. And since XOR operation is just addition modulo 2, it just comes back to itself, and you obtain back the plain text. So let me give an example like this. Assume that your plain text is turned into zeros and ones. Then you beforehand generated a random one-time pad. Assume that it is like this. Now you XOR them. Recall that XOR operation is just column-wise addition modulo 2. So for instance, 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. But 1 XOR 1 is 0. But there is no carry bits. If it was a simple addition, then you will have a carry bit. But now we are simply doing it in modulo 2, so you don't have any carry bits. So this way, although the plain text has some redundancy, but your one-time pad doesn't have any redundancy, it is random. So when you XOR them, the ciphertext actually does not contain the redundancy you have in your plain text. And similarly, the person who wants to decrypt, they receive your ciphertext, they also have the one-time pad, they simply XOR, for instance, 1 XOR 1 is 0, 1 XOR 0 is 1, etc. Okay, so they take the plain text back. So fantastic idea. But the thing is that one-time pad must be truly random. For instance, if you generated deterministically depending on a rule, somebody might guess that rule and capture it, or maybe you use a very basic idea, then people can guess that. And the second thing is that one-time pad can only be used once, hence the name one-time pad, okay? If you use it twice, then we can capture your plain text. Okay? But this is a problem. So let me see if there's an example here. Yeah, okay, so I will talk about it in the 2 slides later. So one-time pad provides perfect secrecy because ciphertext provides no information about the plain text. Instead of working with bits, one can work on letters or characters. Okay, so this can be used in the past. But of course, now we are in a modern age. This is why I always talk about bits. The one-time pad usually printed on a single page with very small letters, hence the name one-time pad. Okay. So the problems are key is too long, because if you want to encrypt 1 terabyte, your key has to be 1 terabyte, right? So it is not practical. Second thing is key distribution. Think about the speed of your WhatsApp messages. If you want to send 10 WhatsApp messages using one-time pad, then you have to beforehand generate 10 many one-time pads and give it to your friend. But in a daily life, you send and receive a lot of messages. So key distribution is a problem. You cannot beforehand generate that many one-time pads and give to people. And the third thing is randomness. So this is not in real world. Actual people do not pay much attention to randomness, but your almost all cryptographic security relies on randomness. In many cryptographic algorithms, I always say that randomly do this, and that has to be really random. If it is not random, then you know you have a problem. And we have many, many examples in the past or also in daily life. And this sometimes happens, instead of using a true random number generator or cryptographically designed secure random number generators, people sometimes use the rand function of C programming language, which actually provides no cryptographic security at all. Okay, so randomness is really important. So let me go back to the key reuse that I mentioned. I told you that you have to use a different key one-time pad all the time. So if the adverse, assume that you use the same key to encrypt plaintext P1 and plaintext P2. Okay, so assume that your one-time pad is K. So you XOR P1 with K to obtain C1, and you XOR P2 with K to obtain C2. So what can go wrong, right? So if the adversary captures two ciphertexts C1 and C2, which we generated with the same key, then they can compute the following. Since they captured C1 and C2, they can XOR it, right? Because they already have C1 and C2. But XORing C1 with the C2 actually means since C1 is P1 XOR K and C2 is P2 XOR K, and XOR is just the addition modulo 2, these Ks actually cancel each other and you end up with P1 XOR P2. So now the adversary didn't capture P1 or P2. They only captured their XOR. But don't forget that the plaintext contains the redundancy of the language or the encoding that you're using. So from here, actually, the attacker can capture part or the whole of P1 and P2. Okay. And this is done, let me see. Okay, not in the slides, but in Second World War, when on a project, you can check the Wikipedia about it. A lot of Soviet communication actually was broken due to this problem. They used the same one-time pad more than once, and Americans actually captured a lot of messages with this. Okay, so as you can see, it is not practical. I cannot use it, but this idea actually introduces us to stream cipher, because stream ciphers try to achieve the one-time pad-like security by generating not random but pseudo-random key stream from a short key. So instead of one-time pad of long bits like K here, you will use a short key, and with that short key you will produce very long zeros and ones, and you will use as your one-time pad and perform the encryption. Of course, it will not be as secure as a one-time pad because you will be generating a very long sequence of bits from a shorter secret key, like 128 bits, okay? But if you can design the algorithm in a good way, then this can provide you very good security, okay? So let me show you what is the difference between a block cipher and a stream cipher. So generally, when we talk about symmetric key cryptography or symmetric key encryption algorithms, also known as private key cryptography, generally we classify them as block ciphers and stream ciphers. So there's a misconception here. People think that block ciphers encrypts blocks, stream ciphers encrypts bits. This is not the correct definition, and it cannot be further from the truth, because most of the stream ciphers actually work on bytes or 32-bit words or even 128 bits. They also work on blocks. So the difference is not about the size of the part you are encrypting. The difference is a little bit subtle, because the difference is block ciphers operate on large blocks of plaintext data with a fixed transformation. Think about AES, for instance. It's just a algorithm that takes 128-bit input and provides you 128-bit output, right? This is a fixed transformation. It doesn't depend on time. It doesn't depend on, how many data you encrypted or anything, right? But stream ciphers are a little bit different because they work on individual plaintext digits, sometimes as small as bits, sometimes bytes, sometimes 32 bits, but with a time-varying transformation, okay? So idea is that it has kind of a memory. It has an internal state and it changes in time. That is the difference between a block cipher and a stream cipher, okay? So everything will be a little bit more clear, but let me try to give the theoretical explanation in a little bit better way. A block cipher processes the plain text in relatively large blocks at a time, and the encryption function is same for every block. A block cipher can be considered as a bijective function, f, which takes two inputs, plain text and the secret key, and produces the cipher text. Some mode of operations, of course, turn a block cipher into a stream cipher. This is why when I talk about counter mode of operation, I told you that this actually turns the encryption into a stream cipher. But when I talk about stream ciphers in more in detail, you will understand why counter mode of operation for block ciphers actually act like a stream cipher. A stream cipher processes the plain text in small blocks, sometimes as small as a single bit. Contrary to a block cipher, a stream cipher has a sort of memory. Generally, we say the state, row T, and I put the subletter T here because at time T, the internal state might be different than time T plus 1 or T plus 2. And it changes as it processes the plain text. This state is an input of the encryption algorithm. We can consider a stream cipher as a pair of functions f and h, as f changes the state. So at time T, the input might be the current state, row at time T. Plain text that is processed at time T, your secret key can determine your next state function. Next state. Okay, this is the F. So this is not about encryption, this is updating the internal state. And encryption function can be represented by H, and it takes again the current plain text and secret key and current internal state and produces the cipher text. This is the general picture. Sometimes your next state function may not use the secret key or the plain text, etc. Okay. So before talking about the stream cipher, first let me talk about something very famous called LFSR, linear feedback shift registers. Because in stream ciphers, as I told you before, these are actually generally used in the past for encryption of data in transit, like GSM communications, Wi-Fi communications, etc. So they have to be really fast. Think about the mobile phones like 15 years ago. They were really bad in processing power, etc. So the algorithm should be simple. So with this simple algorithm, you should be able to generate big data from small data. So these LFSRs actually is used for this. For instance, this is just L-bit LFSR. So there are L-bit boxes here. Each box represents 1 bit. And at a time T, you fill it with some zeros and ones, okay? At time T, it has some state. And when you press a button, it produces 1 bit of output by sending this as the output, okay? And then it will take everything here and shift it 1 bit to the right. So this bit will be empty. And it will be filled by actually performing these XOR operations and then putting the result here. So here I actually put arrows for every bit, but generally these CLs are generally 0. So this bit actually determined by XORing a few of this state. Okay, then you shift it. So important thing is that although the internal state is L bits, now you can produce 2 to the L minus 1 different zeros and ones before it repeats itself. Okay, that is the idea. So you create a large periodicity by using a small device. We call it linear because we are using XOR operation here. If you also add multiplication, etc., then we will call it nonlinear feedback shift register. Okay. So yes, LFSRs are very common in stream cipher designs. At one tick, the register produces 1 bit output. State is shifted 1 bit, and the new bit is obtained by the XOR of the bits of the previous state that has tap point, which are represented here. An n-bit LFSR can have at most 2 to the n-1 different states. So internal part can take 2 to the n-1. We say -1 because if you make it all 0, then it will be all 0, right? So this is why we eliminate that state, and this is why it can produce 2 to the n-1 different internal states. So this means that it can produce 2 to the n-1 output, and then it starts repeating itself. So this is actually the highest periodicity you can get. But if you choose bad tap points, then actually your periodicity might be less than this. like half of it or, some variations. So does it repeat itself after 2 to n minus bits called period? Again, this is the highest period you can get, not you always get this period. Yes, this sentence is important in this respect. Maximum period is obtained when the tap points are chosen according to a degree n primitive polynomial. So actually, we will represent this tap points as the positions that goes to the n degree polynomials, coefficients. But anyway, it is beyond the scope of this talk, but I will give an example here first, and I will talk about it in more detail. But for instance, A51, which is a standard used in GSM communication. So in 2G, this was used. This is still used. But now some of the updated operators use A53, which is actually a block cipher called Kasumi, but it is a modified version of it. And it can also be broken. Actually, this much I show you that in real time, if you have thousands of GPUs, you can practically listen every 2G and GPRS communication, okay? And since it is an academic publication, I put the codes with it. It is available at GitHub, so you can download it and, use it to, I mean, it is illegal, but you can do it, okay? So 2G communication and GPRS is not secure. This is also important because if you use two-factor authentication to receive SMSs, and if you are, not in the city center, most probably you are connected to a 2G base station. So somebody can actually also capture your two-factor authentication by breaking that communication in less than a minute and, use your two-factor authentication to log in to someplace. This is why actually 2G should not be used, okay? With that said, let me go back to our example. So A51 works like this. So this is actually just a key stream generator. So idea is as follows. So this is an LFSR of 19 bits. This is 22 bits and 23 bits. If you sum all of them, it sums up to 64 bits. So idea is as follows. Instead of using a single LFSR, they combine 3 different LFSRs. As you can see, there are different tap points in all of them, but all of them are, primitive polynomials, so they provide the maximum periodicity. So here you get 2 to the 19 minus 1 different output. Here you get 2 to the 22 minus 1 different output, but all of these results of these LFSRs are XORed, and the result is produced as the output. So when you actually call somebody and start talking, your voice is turned into zeros and ones. And that is your plain text. And that plain text is actually XORed with the zeros and ones that is output from here and turned into a ciphertext. Okay? So the person you are talking, also they have the same internal state because they use the same secret key. They also produce this output, but they receive the ciphertext as your voice. Their phone actually XORs your ciphertext with this output here, which we generally call a key stream, and obtain your voice back as the plain text, okay? But this is an example how you can use LFSRs to, design a stream cipher, okay? And this is generally the picture you should keep in mind when you talk about stream ciphers, okay? Yes, I told you that the output here is referred to as key stream. So it may be the case that the next state function does not depend on the plain text. And in this example, in A51, actually, it is like this. It doesn't take the input here in this state. It doesn't care what the plain text is. It simply generates key stream and XORs with your plain text to produce ciphertext. In such a case, the key stream is produced by an output function G. Then the encryption function combines the key stream with the plain text. So next state function simply takes the current state and uses the secret key inside it to turn it into the next state function. And encryption, or the output function here, takes the current state, uses the secret key, and produces the output. And encryption is just H function here. So if you go back to A51 example and look at the next state function, as you can see, it just uses the current state and the secret key. So initially you fill here with the secret key, and there are some also small modifications to it, but with the secret key inside, you actually start running it and produce the key stream, right? So output function here, G, actually just XOR of these 3 LFSRs. Okay? And here the encryption function H is simply the XOR of the output with the plaintext, which is here, not in this picture, but assume that there's a plaintext here and you XOR it with the output, and that is your encryption function. So these are the simplest things you can do. But as I will talk about in the following slides, A51 is badly broken. In real time, you can listen to every A51 communication. Okay. And this can be done by, generating some tables beforehand. You put it into like 4 terabyte or 8 terabyte hard drive, put an antenna next to it with an ARM processor, put it into your backpack, and walk around, and you can listen to everybody. If they're, of course, using 2G. Okay. So this type of stream ciphers are known as key stream generator ciphers. They have the advantage that the key stream can be pro-computed without using plaintext or ciphertext. This can sometimes provide you, reduce the latency and, give you some speed. An important example is the binary additive stream ciphers, where H is the bit-by-bit addition of the key stream and the plaintext, and this was the case for A51, as I mentioned. Block cipher mode of operations like counter mode actually converts the block cipher into a binary additive stream cipher. So think about it. In the counter mode, what we were doing was the encryption of counters with the secret key in using a block cipher like AES, but you end up with outputs which you concatenate to each other and obtain actually a key stream. At this point, you don't need to have the plaintext at all. You can pre-compute this, and when the plaintext is received, you can simply XOR it and produce the ciphertext. So this is why actually counter mode of operation in block ciphers is just act like a stream cipher, and the person who wants to decrypt, they also generate the same key stream, but this time XOR it with your ciphertext to obtain the plaintext. So this is why I always mention that some modes of operation actually turns a block cipher into a stream cipher.